Hi everyone, my name is Satyaam Raha. Welcome back. So, to those who has been following my videos in this playlist serially, so I'm sorry for the late upload. I was a bit sick. I couldn't make the videos. Now maybe I'll be able to continue with the videos. So, uh, we have already completed up to backpropagation, right? You know the concept of backpropagation and how it works. But now let us talk about something which we have been using throughout almost all the videos in this playlist. That is the activation function. So what is this activation function? What should be the properties when we choose an activation function? Can we choose any function as activation function? And what should be the very good properties, very important properties when it comes to activation function? Let us now learn about that. So you can write it down, or you can just keep it in mind. There are two properties when it comes to activation function. Number one, the activation function should be differentiable. Number one, okay, because see, it is very logical. Without a function being able to differentiate, we'll not be able to do backpropagation, right? Differentiation is very much required. uh, you have already seen we differentiated this the loss with the functions, right? So number one is the activation function should be differentiable. Number two, this differentiation should be very fast. Okay, it should not take a long time to differentiate. Otherwise, see, the neural networks are very deep layers, right? It takes almost a very long time to train. And if these functions take a long time to differentiate, you can understand there will be no like use of deep learning if that was a situation. So these two properties should be followed when we come to implement any activation function, right? So in this video I'll talk about two very famous uh, activation function when it comes to neural network. So the number one is the sigmoid function, which we have been using since long from logistic regression, right? If you have watched my logistic regression video, or if you are aware of how logistic regression works behind the scene, you already know that we use the logistic regression, we use the sigmoid function in logistic regression to get rid of the outliers, right? To squash the inputs down to from to 0 to 1, right? To the range of 0 to 1. So let us see why the sigmoid function. See, sigmoid function looks very complicated, right? There is so much complications when it comes to the sigmoid function. But why is it used? I said it should be very easy to differentiate. But why is it used in neural network then? It looks very complicated. So let us see the reason behind it. So I'll just switch up my video and let me take you to the whiteboard. See, I hope my screen is very clear. You can see over here, this is a simple neural network, and this if this fij, this is the activation function, right? This is the activation function. So it can be anything. It can be sigmoid, it can be tan-h, it can be ReLU, whatever, right? But the only condition is this particular activation function should be differentiable, number one. And number two is this particular the activation function should be differentiated very fast. Okay, it should not take much time to differentiate. So now let us see why the sigmoid function. We will talk about two functions here. One is the sigmoid and number two is the tan h. These two functions are very much used when it comes to neural network. We'll talk about these two, okay, and why they are used. These two sigmoid and tan h. You see, sigmoid function has a formula like this. See, sigma, you have already seen it, still I will just write it down. Sigma of z is nothing but e to the power z divided by 1 plus e to the power z. Okay, we can write it like this: 1 by 1 plus e to the power minus z. Okay, so this is nothing but a sigmoid function. So you should wonder, right? I said that it should be very easily differentiable. But looking at this particular thing, it looks like very complicated. How does it satisfy the second property? Okay, that is a very good question. I'll come to that. Now, before doing that, let me talk about the tan z, tan h. So this is tan h. Okay, so if we use tan h of z, it looks like this: e power z minus e power minus z by e power z plus e power minus z. Okay, so this is nothing but the tan h function. So by looking at these two functions, you can see they looks very complicated. Then what is the reason they are extensively used in neural network? How do they satisfy the property of fast differentiation? So now let us look at the properties. Okay, let us look at the properties of sigmoid. See, this is sigmoid. Okay, if you have seen the logistic regression video, you can see this is the squashing function sigmoid, right? It is within 0 to 1. You can see this blue line is the sigmoid line. Okay, and the derivative is also within 0 to 1, and it is always and almost less than the sigmoid. Okay, it is covered by the sigmoid. So this is the property of sigmoid. But now you should see numerically to understand why it is used extensively in neural network. Okay, so you can see, I'll just write it down here. So you see, if we derive, if we find the derivative of this particular sigmoid, okay, this is derivation of sigmoid, right, with respect to z, it is nothing but sigmoid of z multiplied by 1 minus sigmoid of z. Okay, so this is the derivative. This is the derivative when it comes to sigmoid. Okay, derivative of sigmoid with respect to z is nothing but sigmoid of z multiplied by 1 minus sigmoid of z. So you can see one thing. The derivative of sigmoid is in terms of sigmoid itself, right? So what we can do is we can simply implement the sigmoid function once, and we can reuse it both in forward propagation. See, the sigmoid, if we implement it as a function, sigmoid of z, we can use it in forward propagation to calculate the sigmoid value. Also, during back propagation, we can use the derivative. The derivative is nothing but in terms of sigmoid. So we can again reuse the sigmoid function. So this is very easy to implement. Okay, and very fast, because there is no calculation, much calculation required, right? So that is why this particular sigmoid function is very famous when it comes to neural networks. The only reason is it is the derivative of sigmoid is in terms of sigmoid itself. So in backward propagation as well as in forward propagation, we can use the simple function sigmoid. If we have implemented it once, we can reuse it multiple times. Okay, that's why it is very much used when it comes to neural networks. Now obviously you can see one thing: this derivative of sigmoid is always between 0 and 1, right? I'll tell you there is a negative point for this, because the derivative comes in between 0 to 1. But for now you understand why sigmoid is used, right? Now let us talk about the another function, that is the tan h. You have seen the tan h, right? That tan h looks like this. Yes, so now let us look at the tan h function. See, this green line is a tan h function. Okay, it is within -1 to 1. It ranges between -1 to 1, positive 1. Now the derivative of tan h is nothing but it is between 0 to 1. Okay, so the derivative again is within 0 to 1. Max value is 1. Okay, just like sigmoid. Now why is it used so much, right? So I'll write the tan h function again for reference. So sorry, tan h of z was supposed to be e power minus z minus e power minus z. Sorry, I have mistakenly written here. let me just correct it. So it is nothing but e power positive z minus e power negative z divided by e power positive z plus e power negative z. This is nothing but tan h function. Now the derivative of tan h with respect to z is nothing but 1 minus e power positive z minus e power negative z by e power positive z plus e power minus z whole square. This is nothing but 1 minus tan h square. So again, it is logical, right? You can understand that the derivative of tan h is in terms of tan h itself. So if we simply implement the function tan h once, we can use it for forward propagation. This function can be used for forward propagation, and for backward propagation we can simply square it and 1 minus the square of tan z, right? 1 minus tan square z. This is the derivative. So that is why it is widely used, and obviously this again comes between 0 and 1. The derivative is within 0 and 1. Again, this point is a negative point because it comes through from in between 0 to 1, but nevertheless it is very much extensively used when it comes to neural network because of the property that it is in terms of itself, right? So I hope this concept is very clear, and in the next video we'll see the problems that is related to these functions. Okay, there is a function that is an that comes as an outcome to this particular functions, right? This is the it will be creating certain problems when it comes to these neural networks. Okay, because it comes between 0 to 1, the derivative is within 0 to 1. Okay, I'll show you what the problem is in the next video. So till then, thank you for watching. Bye.